Hello and welcome to this video on finding a basis for a given subspace. So in this video, I'm going to start off by defining yet again, and I've done this in several videos in the past, defining what it means for a set of vectors to be a basis for a vector space, and also redefine what it means, what the dimension of a vector space is. And then don't forget too that when I say subspace, like in the title card here, a subspace is just a set that's a subset of a larger vector space or the same vector space itself. But a subspace is also a vector space, right? So I might throw around subspace, vector space, interchangeably throughout this video, and I'm sorry, I hope that doesn't get confusing. Then after the definitions, I'll just go over several examples where I'm given a set that is a subspace of a certain vector space and asked to find a basis for that subspace and then state the dimension. Now I have done this in another video with Euclidean space, R2, R3, R4, whatever, Rn. So the examples I do in this video here will involve other vector spaces, the set of polynomials of degree 3 or less, or the set of 2 by 2 matrices, or stuff like that. Right? Since I've already done a bunch of examples in the past on finding a basis for a subspace of a Euclidean space. So let's begin here. So you've seen this before, hopefully, if you've been watching my videos. If not, here it is. Here's the definition of what it means for a set of vectors to be a basis for a vector space. Right. So a set of vectors, we'll call S, is a basis for a vector space V if the following two things are true or they hold. So one, the set of vectors S spans the space V, or you could say that the span of S equals vector space V. And all this means is that if any vector in V can be written as a linear combination of the vectors in S. And also you must show that in order to be a basis, that the set of vectors S is linearly independent. And what that means is that none of the vectors in S can be written as linear combinations of the other vectors in S. Right. And some people might say too that a basis, the vectors in a basis for a vector space are the building blocks for the vector space. Right. Because you can take these basis vectors and use them to create any vector in the vector space V. Alright, and then at the bottom here, again, probably another definition you've seen in my past videos. The dimension of a vector space V, denoted by dim of V, dimension of V like this, is the number of vectors in any basis for V. Alright. So you've seen in Euclidean space, R2, right, the set of vectors with two components, with two real number components, had a dimension of 2, because the standard basis had the vectors 1, 0, and 0, 1. But again, that's not the only basis, right? I do say any basis here, or a basis, because bases for a vector space are not unique, but just Just know that any basis for a vector space is going to have the same number of vectors in it, and that number of vectors is the dimension of that space. All right, and just recall that a subspace of a vector space is also a vector space itself. All right, so the rest of the video, I'll be giving you, we'll be given a set that is a subspace. Right, so it is told to me that we have a subspace called W of vector space V. Right, so that just means that W is a subset of V, but W also satisfies all 10 vector space axioms. So W is a vector space itself. In fact, recall that to show that a set was a subspace of a vector space, because they're elements of the vector space, 8 of those vector space axioms will automatically hold, like just kind of be inherited from the vector space. You only need to show that it's non-empty and it's closed under vector addition and closed under scalar multiplication. But we're not doing that here. We are told that W is a subspace. Now, if you'd like to verify it for yourself, fine. But we are told that W is a subspace of vector space V, and we're asked to find a basis for the subspace W, and then state the dimension of W. Right. Okay. So we have to find a set of vectors that span W and that are also linearly independent. All right, so my first example here, we're working with our vectors are these polynomials that are degree 3 or less. Remember this, the larger vector space V is this fancy P3. And hopefully you recall that this is the set of all polynomials of degree 3 or less. Okay, so let's keep that in mind, because you're going to see in every single one of these examples, when I go to try to find a basis for a vector space, I'd like to take a look at what a general vector looks like from that vector space. So if we know what kinds of vectors we're dealing with, right, these polynomials of degree 3 or less, I can more simply describe them in some general way, as we'll see here in a minute. Alright, so W, right, is a subspace of P3. Right, so W is also a vector space, and it's made up of polynomials from P3. Right, so the vectors in W are polynomials of degree 3 or less, but only polynomials, though, that satisfy the following condition, such that the value of the polynomial at input of 0 is 0, and the value of the polynomial at 1 is also 0. So before I even get into finding a basis, I do like to just think of, are there actually, can I think of any vectors that would be in W, right? I know they said it was a subspace, so it's non-empty, right? So we know there should be some vectors in here. But I'm going to just go through and let's see if we can find some examples of some vectors in W before I go find a basis for it. So again, they're just polynomials with degree 3 or less, such that when I plug in 0, I get 0 as an output. When I plug in 1, I get 0 as an output. Well, if I plug in 0 to a polynomial and get 0 as an output, that means that x is a factor. And if I plug in 1 and get 0 into a polynomial, that means x minus 1 would have to be a factor of the polynomial. So x squared minus x. This would be in W. There's a polynomial of degree 3 or less. Right, it's degree 2. that when I plug in 0, I'd get 0, and when I plug in 1, I'd also get 0. So there's one vector. I mean, I could multiply this again by x and get x cubed minus x squared, right? This, when I plug in 0, gives me 0. When I plug in 1, gives me 0. That belongs to W. You know, again, since I know it's a subspace, right? It's a vector space. It should be closed under vector addition, right? So if I were to take these two vectors and add them, you know, that would give me x cubed minus x. This should be in W as well. And let's see, I plug in 0, I get 0. Plug in 1 here, I get 0. It's also closed, it should be closed since it's a vector space, it should be closed under scalar multiplication. So say I take this first one, multiply it by 3. That'd be 3x squared minus 3x. That belongs to W, right? It's a polynomial degree 3 or less. When I plug in 0, I get 0. If I plugged in 1, it would be equal to 0 as well. And many more, right? I could do all sorts of, multiply any of these by a scalar, add any of the vectors I find together to get another vector, and you know, I could do that all day long. And of course, the 0 you know, just 0 belongs to W2, right? You know, if I plug in 0 to 0, I get 0. I plug in 1 to 0, I get 0. And again, the number 0, you could say, has really any degree, so it really has an undefined degree, so you can always include 0 as a polynomial of degree 3 or less, right? You could think of 0 as 0 plus 0x plus 0x squared plus 0x cubed, right, as a polynomial of degree 3 or less. But yeah, so there's tons of vectors in here, right? Tons of polynomials. The question is, though, you know, what are the building blocks? You know, what are polynomials I could use to make any of these, right, with just some linear combinations, right? All right, so this is where the concept of, you know, what does a general vector in the larger vector space look like, and then we'll look at the subset and see, you know, what vectors from here are actually in W, you know, satisfy the conditions. So polynomial, like I said, this is this, you know, this P3 that everything's a part of here. What do these look like? All right, so a general vector from P3 looks like the following. I'll say, you know, I'll use P of x, okay, just so we have a function notation here. P of x equals, and then again, it's a polynomial of degree 3 or less. So you'll have some, you know, some scalar a1, and I'll say a0, some constant term plus then some first degree term, say a1 times x to the first, plus and then some second degree term, say a2 times x squared, and then plus some third degree term, you know, say a3 times x cubed, and that would be as high as it goes, right? Where say a0, a1, a2, a3. Let's just say these are polynomials with real coefficients, right? It wasn't stated, so let's assume that the coefficients of the polynomials have to be real numbers. So this is what every polynomial, this is what every vector in P3 looks like. But now we're going to say, okay, now which of these vectors actually belong to W? Right. So remember my polynomials here, and I'll write it again over here so maybe it's more visible. So in W, my polynomials look like this. You know, again, a1, said a1, a0, right, plus a1x plus a2 x squared plus a3 x cubed. But, you know, with these conditions, right, these conditions have to be satisfied. So such that, you know, p of 0 equals 0. Well, if I replace x with 0 here, I'd have 0 on the left, you know, p of 0, and all the terms with x in it would disappear. So this would simply tell me that the value of a0 is equal to 0. Alright, so for every polynomial in W, this is saying that the constant term is 0. And you could probably have guessed that. So this is the constant term in any polynomial in W is 0. And again, like I said, you probably could have guessed that by just looking at some of the examples. The 0, this x cubed minus x, 3x squared minus 3x, x squared minus x cubed minus x, where all these polynomials in W here have a constant term of 0, and that's basically what I'm just saying here. Right. But not only does it have to satisfy, this polynomial degree 3 or less, has to satisfy that first condition, but it also has to satisfy the other condition. Right, so the value of p at 1 is also 0. Alright, so popping this stuff in. Now if I plug in 1 for x on the left, that's p of 1, that should be 0 equals, and then when I plug in 1 for x on the other side, I get a0, but again, we know that a0 is 0. So I really don't need to write it. I'll block it. I'll get rid of it in the next line. Plus, and then I'm replacing x with 1 everywhere, right? I'm plugging in x. So there's plus a1, plus a2, plus a3. Because 1 squared, 1 to the first, 1 squared, and 1 cubed are all 1. Alright, and then a0 is 0, so I'm getting this equation. So a1 plus a2 plus a3 is equal to 0. Okay. Alright, and then do you see what I got here now? I actually have a system of linear equations. Right, here's the system. Both of these conditions applied to my general vector lead me to a system of equations involving a0 through a3. They lead me to this system where, again, I'll just write the equations again, where a1 plus a2 plus a3 has to be equal to 0, and a0 has to be equal to 0. Now I guess, if you wanted to write this as a augmented matrix like we're used to, down the first column I'll put the coefficients of a0. Alright, so that would be 0, 1, right? There's no a0 in the first equation, 1a0 in the second equation. Down the second column, the coefficients of a1, so 1 and then 0. Then the coefficients of a2, 1 and 0. The coefficients of a3, 1 and 0. A little bar, and the zeros on the other side, right? Equals, and 0 on the other side. And then I put this in reduced row echelon form. Now that would be very simple. In fact, I don't know why I wrote it this way. If I switch the rows, it'll be in reduced row echelon form or reduced echelon form. So 1, then a bunch of zeros, and then 0, 1, 1, 1, 0. Alright, so looking at this, that first row, alright, we already know this, tells me the value of a0 is 0, right? I already mentioned that the value of the constant term in any of these polynomials is going to be 0. So we know, and then looking at the pivot columns as well, right? This is a pivot, has a lead 1. This is a pivot, has a lead 1. So a0 is basic, and we already know its value, right? a0 is 0. a1, right? a1 was the coefficients of x to the first, right? The coefficients of x to the first. a1 is also basic. And then you see these last two columns here don't have a pivot right before the equal sign. So A3, A2 and A3, the coefficient of the x squared term and the coefficient of the cubic term are free, meaning I can let those be any value I wish. All right, I can let those be any value I wish, and then we have the A0 and A1 have to be fixed. A0 is always 0, and then when I pick values for A2 and A3, we know what A1's got to be. So the solutions of this system, right, again, I'm just going to let, because these are free, and I personally like doing this for free variables. You can leave them as they are, A2 and A3, but I like replacing free variables with other expressions that can take on any real number value. So I'm going to let A2 be the number t and A3 be the number s, right? Or you could where s and t are any real number, right? Okay, so from this line we're getting A0 equals 0, and then from the second row we're getting that A1, right, A1 the basic variable, plus A2, which is now t, plus A3, which is now s, should be equal to 0. So we're getting that A1 must be equal to the opposite of t and then minus s, right? Just subtracting t and s from both sides. So putting this all together, the solutions of this system look like this. A0 we know is 0. A1 is this negative t minus s, and then A2 is t, A3 is s, and maybe I should have put those in the other order, alphabetical order, but sorry about that. And this is again for any choice of s and t, right? So this tells me this is giving me a description of the coefficients of any polynomial that belongs to W. All right, so back to the polynomials in W. Right, they looked like this, right? I said they had to look like this, but satisfy these conditions. All right, so polynomials that look like this, but satisfy these equations, satisfy this system, belong to W. All right, so let me put that all down here now. All right, so the vectors in W, right? The vectors, the polynomials in W look like the following. We had A0 plus A1 times x plus A2 times x squared plus A3 times x cubed, but these conditions have to be met. They have to satisfy this A0, A1, A2, and A3 have to satisfy this system that we wrote in order to be satisfying the conditions and being inside set W. So I make all these replacements, right? So this would be equal to A0 is 0. A1 is negative t minus s times x, right? Plus A2 is just t, and then times x squared, and then A3 is s, right? So plus s times x cubed. Now you might remember back from when we were finding bases for subspaces of Euclidean space. What you're going to notice is that the number of free variables here, and I'll write this note later, the number of free variables, the A2 and A3, which I called t and s, will give me the number of vectors that will be in a basis for the subspace. And here's what I'm going to do here. Watch. See, I'm going to have some stuff with t attached to it and stuff with s attached to it in this polynomial. So let's break this up. I'm going to distribute the x here, And I'm going to gather all the terms with one free variable, and then gather all the terms with the other free variable, the t and the s. Right? So I have negative t times x, and then minus s times x, plus t times x squared, plus s times x cubed. And then gathering the terms with t, we have t multiplied by, negative x plus x squared, or x squared minus x. Right, that's x squared minus x, with the ones with the free variable t on it. Plus, and then the ones with free variable s on it have negative x and then plus x cubed, so x cubed minus x. Right? And what this is saying, right, is that we have these are real numbers, scalars. We're saying that every vector in W, every polynomial in W, is a scalar times this polynomial plus a scalar times that polynomial. So it's a linear combination of these two polynomials. Right, so what this line is telling me is that every vector in W, every polynomial in W, is a linear combination of x squared minus x and x cubed minus x. Oops, sorry. The word combination got cut off there. I apologize. So that means that W is spanned by these two vectors. So that means that the set with these two polynomials, x squared minus x, comma, and then x cubed minus x, spans W. Right? Every vector in W, every polynomial in W, we have seen can be written as a linear combination of just these two. Or another way of saying that is that the span of this set, the set with x squared minus x and x cubed minus x, is equal to W. All right, so that's great. And now the question becomes, yeah, the set spans W, but now the question becomes, is this set of vectors independent, right? And I've done plenty of other things on independence, checking for a set is independent. You could do the lawn check where I take a scalar, where I take this equation here, take a linear combination, take a scalar times x squared minus x plus a scalar times x cubed minus x, and set it equal to 0, right? The 0 vector, or the 0 polynomial here. And you'll see that the only solution to that would be if t were 0 and s were 0 would be the trivial solution, right? So these are independent. But another quick check too is, remember, when you have a set of only two vectors, they're independent if they're not scalar multiples of each other, right? If one can't be written as a scalar multiple of the other. And yeah, you could multiply this by any scalar you want, and you're not going to get an x cubed term. So you can't write this second vector as a scalar multiple of the first vector, and vice versa, right? You can't multiply this by any scalar and get an x squared term, right? So these aren't scalar multiples of each other. So not only does the set span W, but that set of two vectors, the set of those two polynomials, x squared minus x and x cubed minus x, is linearly independent, or I'll just say independent. So after all is said and done with this, this first example, this set with x squared minus x and x cubed minus x is a basis for W. Right. Okay, so I guess the note I also wanted to make too here, back on the system was that the number of free, remember these were from the free variables t and s. You'll notice that when you try to find a basis, just like when you were trying to test for if a set spans another vector space or if a set was linearly independent, a lot of stuff in this linear algebra teaching, a lot of stuff in linear algebra courses just boils down to solving a system of equations. You saw it here. There was another system of linear equations. And in that system, you will see that the number of free variables that shows up in that system that you eventually set up will be equal to the number of vectors in a basis. Alright, so that'll be something nice to know for future examples. Right? Which we saw here, right? There are two free variables, s and t, two vectors in my basis for w. Alright, so let's go back and look at w again right here. So here was w. Alright, it was a set of all the polynomials degree 3 or less such that these two conditions held. Well, what we're saying here is that here's the building blocks for this set. Every polynomial in this set I can construct by just finding a linear combination of these two. Right? And they're independent. And look, I mean, so you see here, well, there they are right there, x squared minus x, x cubed minus x, right? And I could take, this vector here minus this vector here and get this, right? Again, let's just take a linear combination of these two to get this. Take none of this plus 3 of that and get this, right? You can take, again, every vector in W is built from these two, if that makes sense, right? They're like the building blocks. Alright, and now that I have a basis for W, then the dimension of W is, again, just the number of vectors in a basis, so 2. This is a two-dimensional vector space, this set W. Alright, and you might think, hey, well, again, just don't jump to the, remember the vector space P3, remember the dimension of P3 was 4, right, the larger vector space. So you're going to see that any subspace is going to have a dimension that's less than or equal to the space that it's a subset of, right? W is a subset of P3. Since the dimension of P3 is 4, and W is a subset, the dimension of W should be, 4 or less, which it was here, and it's 2. If I, for some reason, ended up with a dimension of 5, then I know I did something wrong. Okay. So, yeah. So, again, just to recap what happened here, I'm given a subspace of a vector space. First, I'm going to look at what do all the vectors in that vector space look like, and then which ones of these would actually satisfy conditions to be in my subspace. And I want to eventually get down to the point where I write a vector in my subspace, what it looks like in general, as and we're going to try to write it as some linear combination of a couple of vectors, right? And then that couple of vectors would span the space, and then you'll check to see if those vectors are independent, and they should be usually if you do things correctly. But we'll still check if they're independent afterwards. All right. So now my next example. Again, I'm told that this is a subspace of the set of 2 by 2 matrices, right? Remember the set of 2 by 2 matrices was a vector space, right, under standard operations, standard matrix addition and scale multiplication. And perhaps you might recall that the dimension of the set of 2 by 2 matrices with real entries was 4, right, just 2 times 2. So when we're done here, the dimension of W better not be greater than 4, right? It's going to be 4 or less since it is a subspace. And again, I'm told it's a subspace. Alright, now again, let me just like I did last time, and like I usually like to do when I'm given a subset of a space. Let's think of some vectors that would be in here before I go into talking about what the general vector in there looks like. I mean, you already see what the general vector looks like. They gave it to us. So here are some vectors in W. Now the vectors this time are 2 by 2 matrices instead of polynomials like before. So some vectors in W. Now obviously, again, I got the first row, first column entry has to be 0. And then the first row, second column, and second row, first column entries have to be the same according to this, right? AA, where A is any real number I want. And then the second row, second column entry can be anything I want. This is B. So 0, 1, 1, 3. That's in W. Of course, the 0 matrix would be in there. Right, just let A be 0 and B be 0. That belongs to W. 0, -2, -2, 15. Right? It doesn't matter what that last lower right corner is, as long as the upper right corner and lower left corner are the same. The upper left corner is 0. You're golden, and so on. So there's plenty of vectors in this set, right? Plenty of matrices, and again, the question is now. I'm going to do the same thing I did last time. Now it's pretty obvious what the general. I mean, they tell me what the general vector looks like, right? But I'm going to do what I did kind of with just how I would generically go through these. The larger vector space, that this is coming from. What does every vector look like, right? Every vector in R, 2 by 2 looks like this. It's a 2 by 2 matrix. And so I've got 4 slots to fill in. They say this is A1, A2, A3, and A4. All right. Every vector in R2 by 2 looks like this. And A1, A2, A3, A4, those are just numbers, right? Real numbers. Well, in W, right, if we're in W, a vector from R2, 2, right, from R2 by 2, right, this guy over here, again, A1, A2, A3, A4, has to satisfy the following conditions. And this is where the conditions, like in the first example, it's in the conditions that need to be satisfied to be in the set W. That's where we're going to get our system of linear equations from. It has to satisfy the following. A1 needs to be 0. Right, the first row, first column entry needs to be 0. All right, here's the system. A2 and A3 need to be the same. And that's it. All right. So what you're going to see here is A4 is free. A4 is free. And additionally, you'll see that one of the A2 or A3 will be free as well, because again, you see how there's 2 variables up here in this. I mean, again, like I said, I could have done this much more easily by looking at this, and I will in a second after I do it this way. So the system here, if I get it the way we like it, where all the variables on one side, constants on the other, so I can write a augmented matrix. We have A1 equals 0, and A2 minus A3 equals 0. And don't forget there's A4 involved. All right, don't forget there's A4 involved. So when I write my augmented matrix, down the first column, the coefficients of A1, which would be 1 and then 0. Down the second column, the coefficients of A2, 0, then 1. Then the coefficients of A3, 0, then -1. And then again, don't forget there's this variable a4. The coefficients of a4 are 0 and 0. Right? There's no a4, no a4, and then equals, and then I got the zeros over here. And this is already, if you can recognize it, this is already in reduced row echelon form or reduced echelon form. All right. So I looking for my pivot columns. Right. This is where the lead ones are. There's a pivot in this column. So A1 is basic. There's a pivot column for the second column that was corresponding to the coefficients of A2. So A2 is a basic variable. And then these last two columns here before the equal sign, right? The coefficient, my coefficient matrix. The last two columns of my coefficient matrix aren't pivot columns, so they correspond to my free variables. A3 and A4 are free. So just like the last example, I have two free variables, which will tell me, indicates to me that there are going to be two vectors in my basis for W when I eventually find a basis. Alright, so as I do with free variables, I'm going to replace them with something. This time I'll do it in alphabetical order more properly. So let's say A3 is the number S, and A4 is the number T, where S and T are any real number I want. Right, they can be anything, they're free. Alright, now from the first line, we're seeing that the value of A1 is equal to 0, so that's never changing, right? That's this first row, first column entry, right, which we see up here, right? It has to be 0. Then the second row tells me that A2, my basic variable, minus A3, so minus S, plus no A4, so nothing to worry about there, equals 0. So A2, must also equal S. Right, so this, and then A4 is just this value T, right? So the solutions of this system, A1 equals 0, A2 equals S, A3 equals S, and A4 equals T. Well, you know what? If I just called them A and B instead of S and T, I'd get exactly the same matrices that are described up here. All right, let me show you. So my general matrix from R2, right? So remember this is from R, so A1, A2, A3, A4. If it's going to be in W, right? If it's going to be in this set, would look like A1 is 0, A2 is S, A3 is S, and A4 is T. And do you see how it's kind of silly that I went through all this? See how this looks exactly like they already gave me, but instead of S's they have A. I could have just called the free variables A and B instead, right? And then just like in the last example with the polynomials, I now have these two free variables, this S and T. I would like to separate it into, term with S plus a term with T. All right, separate it. So and write this matrix here as a linear combination of two matrices, right? Again, one with a coefficient of S, one with a coefficient of T. So this is using matrix addition here, and it's, remember, to get it to split up a 2 by 2 matrix, I have to write it as a sum of two other 2 by 2 matrices. Again, one involving S, so there's no S in the first row, first column, then you have a S, S, and then there's no S in that second row, second column term, and then add to that another 2 by 2 matrix, right, where you're involving the T's, where there's no T in there, no T there, no T there, and then one T there. Then using the scalar multiplication property of, properties of how you do scalar multiplication for matrices, I could pull, all these have S in common, I could pull S out. And you have 0, 1, 1, 0, right? If I multiplied this matrix by scalar S, you'd get 0s as 0 back, plus pull the t out of this one, the other free variable, and then you'd have 0, 0, 0, 1. And so what we're seeing here, and again, I could have done the same thing with A and B, split this up to 0A, A0 plus 0, 0, 0B, and then pulled A out, pulled B out. So I could have done that just from the get-go instead of setting up all this system, but I still want to show you that you can set up a linear system for any time you're trying to find a basis for a subspace. All right, so what we're seeing here is that any vector from W, right, any vector, any matrix from W is a linear combination of these two vectors, right? It's a scalar times this 0, 1, 1, 0 vector plus, and then a scalar times this 0, 0, 0, 1 vector, these two vectors. So this 0, 1, 1, 0 and 0, 0, 0, 1. So what that tells us is that this set of vectors spans W, right? This tells me that the set of these two vectors, right, 0, 1, 1, that 2 by 2 matrix, and 0, 0, 0, 1, tells me that this set spans W. Right? Every vector in W can be expressed as a linear combination of these two. So check on that. Additionally, this set of vectors is linearly independent, because again, there's only two of them. Right? There's only two of them, and when there are only two vectors, they'll be linearly independent when they're not scalar multiples of one another. So if you see this, if I took this vector, you couldn't multiply this matrix by any scalar to get this, because you multiply it by any scalar, that second row, second entry, second column entry is going to always be 0. You'll never make it into 1. So these aren't scalar multiples of each other. So these are also independent vectors. Sorry, I should say the set is independent. Check. Alright, so this set of vectors, the set with these two matrices, is a basis for W. Alright, I'm going back to looking at W again. Alright, so that means that any vector in W, this is like, again, the set of building blocks. I can use these two matrices to make any matrix in W. Right? Think about it. How about that one there? If I took, this matrix plus 3 of that one, I'd get this one that I wrote up earlier. This one, I just take 0 of both of them, get the 0 matrix. This one, if I took -2 times this matrix plus 15 times this matrix, I'd get that matrix. And anything like that, right? You can use these two to build the entire space called W. Right. And just like the first example, right, this basis for W had 2 vectors in it, so the dimension for W is 2. It's another 2-dimensional vector space. All right. Next example. Got a few more. All right, so this one, I think I'm bringing this example up for a reason. Because I didn't address it as much as I should have in the videos on Euclidean spaces that I've made. All right, so here again I'm given we're looking at that set of 2 by 2 matrices, that vector space again. And here W is a subspace of this 2 by 2 matrix vector space. So here's how W is made up. All right, W is made up of all matrices that look like this, that satisfy this condition. All right, where if I take, so any matrix such that when I multiply it by the 2 by 1 matrix, with the 1, 0, I get the 0 matrix, the 0, 2 by 1 matrix back. All right. So as before, let's see if we can find vectors in W. Are there any? And there should be, right? It was said to be a subspace. So are there any vectors in W? All right, so I'd have to really think about when is this condition holding. All right, well, think about this. If I multiply these two matrices, 2 by 2 times a 2 by 1 is going to be a 2 by 1. And the first row, first column entry is going to be A times 1 plus 0 times 0, so A. And then the first row, second row, first column is going to be negative A times 1 plus 2A times 0, so just negative A. And this has to be equal to 0, 0 in order to be in this set. All right, in order to be in W, well that I mean, look at it. The only way two matrices are equal is if their elements are equal, their corresponding elements, corresponding entries. So A has to be 0, and that's it. That is, that's the only solution here. Okay, so if the only value A can be is 0, so A is not free, like in the last example where you had some variables and like they all represented free variables, right? They could be anything you wanted. If this condition has to be met, then the value of A can only be 0. So there are no free variables here. A has to be 0. There are no free variables in this problem. So that means that there's going to be no vector in a basis for W. So the empty set, what we're going to see here eventually, right? I'll get to it. But what we're going to see here eventually is what's called the empty set, or the set with nothing in it, right? No vectors, is the basis for W. Right, but we'll get to that in a second. But because A is the only vector in W is this 0 matrix, according to what I saw over here, right, where I replace A with 0. So we could also just say that W is this set. And that means exactly the same as all this. All right. And I had brought it up in the videos on Euclidean space. If you've seen those, that the set with only the 0 vector in it, or only the additive identity, is a subspace, but it is said to have dimension 0, right? Because again, there are no free variables here. So yeah, I'll make that note again. Right? The subspace, the set with just the 0 vector in it, or just the additive identity, because remember, this might not always be all zeros. It could be it depends on how vector addition and scalar multiplication are defined. But the set with just the additive identity in it, right? The 0, the 0 vector thing called the 0 vector, that subspace is defined to have dimension 0. A dimension of 0. All right, so the dimension of W equals 0, and then when you talk about a basis for W, right, a basis for W then would be what's, you could just say it's the set with nothing in it, or this like slash circle with a slash through it. This is called the the empty set. All right. And you might be thinking, hey, wait a minute. What about the set with the zero matrix? Isn't that a basis? This would not be a basis. Remember now, sure, it spans W. Fine, right? Because any linear combination of this vector, any scalar multiple of this vector is still this vector, right? So it's closed under scalar multiplication. It's non-empty. But is it independent, right? Is this set with 0, 0, 0, 0, 0, 0 there independent? No. Remember, any set with the zero vector in it, any set where you have the zero vector inside of it, is dependent. That's something, again, that you've seen from a separate video of mine on linear independence and independence, if you've been watching or reading. So because this set isn't independent, you can't call it a basis for the set with just the vector in it, right? Just the zero vector in it. All right, so this one was a bit tricky. Because if you end up with a subspace with just one vector in it, right, and typically that'll be the only time you're going to have a subspace with a vector is if that vector is the additive identity. They would say that has dimension 0 and a basis of the empty set. So this was a bit of a tricky one. Now, if I went through and did it the way I was doing it before, try to set up like a system of, really the system of equations would end up boiling down to like this, like I had here. But let me show you. Let me try going through it the way I did before, right? Where I say, hey, my larger vector space, the vector space that this is a subset of, that W is a subset of, is R2 by 2. And I think, what does every vector in R2 by 2 look like? Well, I'll put it up like I had earlier, A1, A2, A3, A4. But to be in W, for this to be in W, we'd have to have we'd have to have the following things be true. So let's say I stick A1 to where it is. A2 would have to be 0, right? A2 would have to be equal to 0. A3 would have to be the opposite of A1, right? This entry here would have to be the opposite of that entry to satisfy this condition. A4 would have to be twice A1, right? The lower right entry would have to be twice the upper left entry. So A4 would have to be twice A1. And on top of this, we'd have the product of this matrix A1, A2, A3, A4. Time, this I'm talking about this condition now. Right, times that column 1, 0 would have to be equal to 0, 0. And this will add some more equations to my system. And just as before, when I multiply these two, I'd get the A1, A3. Right, if you multiply this 2 by 2 by this 2 by 1. And that has to be equal to 0, 0. And so A1 would have to be equal to 0, so I pop that in here. A1 would have to be equal to 0, and A3 would have to be equal to 0. And what you're seeing is that the only vector, like, you look at this, this is a system of equations. Right? This is a system of equations. But you can see that A1 has to be 0, A2 has to be 0, A3 has to be 0. And if A1 has to be 0, then A4 has to be 0, right? You're seeing the only solution to this system. There are no free variables, right? Only solution. I could write a matrix for this, but it'd be really silly. it would be a silly matrix. But it's obvious, this one. The only solution to this system is A1 equals 0, A2 must be equal to 0, A3 must be equal to 0, and A4 must be equal to 0. And no free variables. Right, and so as I said earlier, W, right, the only vector in W is where A1 is 0, A2 is 0, A3 is 0, A4 is 0. That's the only vector in W. And as I mentioned before, right, a subspace with only one vector in it, that additive identity, has a dimension of 0 and no basis. Right? Again, basis is that empty set, a set with no vectors. Right? Again, you could have done it that crazy long way, but really just looking at this condition, I figured that out earlier. Right? That only the additive identity, only the 0 vector is in this space. So it'll have a dimension of 0, and yeah, but this is a huge note right here. Okay, keep this in mind. As you've seen with this example, this can happen, right? You can have a subspace that's only consisting of the identity, the additive identity, the 0 matrix, the 0 vector. Right? Okay, all right. So I don't have that happening anymore, I hope. I picked some other examples. All right, so I've got just two more. All right, so now we're back into polynomials here. All right, back into polynomials. So W is a set of polynomials of degree 2 or less. All right, and they're polynomials that satisfy the following condition. Now you gotta think, oh, calculus, derivatives. Hopefully derivatives of polynomials aren't something that's too challenging for you, or you remember very easily, right? Power rule for derivatives and everything. So in W, you have all the polynomials of degree 2 or less that satisfy the following. The value of the polynomial at 5 minus 3 times the value of the derivative of the polynomial at 5 plus 2 times the second derivative of the polynomial at 5 is equal to 0. And I'm told, right, this is a subspace of P2. All right. So what we're trying to do is find a basis, right? Now the dimension of P2. And again, if you recall from another video, dimension of these sets of polynomials of degree n or less, the dimension of P2 is 3. All right, because you have a standard basis of 1x and x squared, basis with 3 vectors that are for P2. So the dimension of W had better not be 4 or 5 or something, right? It better be 3 or less, right? 3 to 0. Okay, so just as I've been doing with all these examples, look at P2. So what does any vector in P2 look like? Well, it's a polynomial of degree 2 or less. So I've got a0 for some constant term plus a1 times x for some linear term plus a2 times x squared for the degree 2 term, and that's it. Where a0, a1, we'll just say these are real coefficients, okay? Now to be in W, I'll call this p of x. Right? So any polynomial in P2 looks like this. Right? But to be in W, what has to happen? Not only do you have to look like this, but you have to satisfy this condition. Right? So this is where, again, this is where the system comes up. Well, let's see. Let's go. So if I have p of x and equals a0 plus a1x plus a2x squared, that's just a, we'll see. What we're doing here is we're also involving the derivative and the second derivative somehow. So remember, p prime would just be, the derivative of a constant is 0, and this would be a1, and then power rule, you got plus 2a2 times x, and then also involving the second derivative would just be, that's 0 again. That'd just be 2a2. All right. So the value of p at 5 would be, pardon me, a0 plus 5x, 5a1, I'm replacing x with 5, plus 25a2. And the value of the first derivative at 5 would be a1 plus 10a2, right? 5 times 2, a2. And then the value of the second derivative at 5 is 2a2. Right? And what we're seeing here is, I'm going to plug these into my equation, my condition, and what we're going to see here is a system of linear equations involving a0, a1, a2, but when I say system, I really only mean one equation. We're going to get one equation with these three unknowns, a0, a1, and a2. And I can make a matrix for it and stuff like that if you want. But so we have P of 5, right? I have a0 plus 5a1 plus 25a2. That's the value of any polynomial here at 5. Minus 3 times p prime at 5, a1 plus 10a2, and then plus 2 times the value of the second derivative at 5, which would just be 2a2. This must be equal to 0 if we are to have a vector in W, right? If we have a polynomial that actually belongs to W. Alright, so what I'm going to do is I'm going to gather some like terms here. There's only a0. There's only one a0. Now the a1s, there's a 5a1 there, then minus 3a1. Right, when I distribute the negative 3, that's all for the a1s. 5a1 minus 3a1 would be plus 2a1. And then there's 25a2 minus 30a2. Right, that's triple underline. And then plus 4a2. So 25a2 minus 30a2 would be negative 5a2. And then plus 4a2 would be minus a2. And this must be equal to 0. And you see, this is my system. I know there's only one equation here, but this is the condition that needs to hold for our coefficients for a0, a1, and a2 in order for our polynomial p of x to be in set W. Alright, now I know this is silly looking, but if you made the augmented matrix here, it would look like this. Just a 1 by 4. You have coefficients of a0, 1. Coefficients of a1, 2. Coefficients of a2, negative 1. Bar, 0 on the other side. And this, has a leading 1 already. This is already in reduced or echelon form. Alright. It's very silly. But just looking at it the way I've been doing. And then it has, the first column has that leading 1 in there, so that's a pivot column. So a0 is basic. And then these other two columns, again, just for the coefficient matrix, these other two columns are not pivot columns, right? They don't have that leading 1. So a1 and a2, the coefficients of x and x squared, are free. And this time, I'll do it again, where I call a1 s and a2 t, where s and t are real numbers, just like I've been doing for other free variables, right? And then this row, the only row, tells me I'm just replacing a1 with s and a2 with t. So I have a0 plus 2s minus t equals 0, and we're getting a0, the constant term, must be t minus 2s, or negative 2s plus t, just subtracting 2s, adding t. So the solutions of this equation, this system with one equation. So the solutions of this are a0 equals, again, t minus 2s, a1 equals s, a2 equals t. And then I pop these into what my polynomials in W. So we'll get what a polynomial in W looks like. All right, so a vector in W, a polynomial in W, will look like this. You have a0 plus a1x plus a2x squared, right? This is just a generic degree 2 polynomial or less, but I pop these in, these are the conditions that need to be met in order for the polynomial to be in my set W. So a0 is, t minus 2s, plus a1 is s, so plus sx, plus a2 is t, plus tx squared. And then just as I did in the past, I got these two free variables, so you're going to see two vectors showing up in a basis for w. And I'm going to write this vector from w. I'm going to take any vector from w and express it as a linear combination of two vectors, two variables. And again, so far we've seen examples with 0 free variables, 2 free variables. You might have just 1 free variable or 3 free variables, right? Just because I have a lot with 2 here doesn't mean there's going to be 2 all the time. All right, and then I'm going to split it up to the terms with the one free variable. There's negative 2s plus sx, right? And then plus, and then the terms with t's, I'm going to gather together t plus tx squared. Factor out the free variables. You have s times, and then x minus 2, right? Negative 2 plus x, plus, and then factoring out the t, got 1 plus x squared, or x squared plus 1, whatever. Okay. So what we're seeing after all this, and you know what? I didn't. Well, probably because it was a hard thing to think of. What are vectors that actually satisfy this? What are polynomials that satisfy this? It's kind of difficult to think of. But we can see now, right? This line here tells me that every vector in W, every polynomial in W, is a linear combination of these two polynomials, right? Of x minus 2 and I'll put it in descending order: x squared plus 1 plus x squared, right? So these are going to be the building blocks for W, right? Every polynomial in W, every polynomial, every degree 2 or less polynomial that satisfies this equation, right? This with derivatives and everything, is going to be a linear combination of these two. So x minus 2 satisfies that, and you can check it out. X squared plus 1 will satisfy this. You can try that out on your own as well. And any linear combination of these two will also satisfy this equation with the derivatives, where you're plugging in 5 and stuff. All right, and again, there's only 2 of them. So these two vectors span W, and they are also independent, because again, there's only 2 of them, and when there's only 2 of them, you need to just check if they're scalar multiples, and they are clearly not. So this set is a basis for W. Right, so the set with x minus 2 and x squared plus 1. All right, this set is a basis for W. The building blocks of W, right? And then the dimension of W then is 2. All right, so here it is, yet another example of a two-dimensional vector space. This description here, this W, is a two-dimensional vector space. All right, I have one last example involving some matrices again. Another example involving some matrices. So here the vector space, the vector space at large this time is the set of 3 by 3 matrices. So W here is the set of all matrices called A, all 3 by 3 matrices A, such that A is a diagonal matrix. Right, a diagonal matrix. Now remember, a diagonal matrix has entries. Just basically every entry that's not on the main diagonal is 0. All right. So let me just give you some examples of, here are some vectors. This one I can actually think of. It's not as hard as the last one. Vectors in W. Right, here are some vectors in W. 1, 2, 3 down the main diagonal, and 0 everywhere else. That belongs to W. Negative 5, 7, 1, and then 0 everywhere else. lots of them. All right, you can think of a million things. Just as long as the entries that aren't on the main diagonal are all zeros. Now you can have zeros down the main diagonal too. I mean, as long as the ones not on the main diagonal are all zeros, it's still considered a diagonal matrix. This belongs to W as well. You could think of a million things. All right. Okay, so like I've been doing, we want to find a basis. So what are the building blocks? Some building blocks for this space W. All right, so like I've been doing, like look at the vector space that it's a subset of R3 by 3. What does this look like? So a 3 by 3 matrix in general with real entries looks like you have some real number. Nah, I could do A1 through A9. I'm just going to do A, B, C, D, F. Again, I don't like to write E because the number E, right? 2.718 and so on. So E, F, G, H. And again, I don't like to write I because people often confuse that with the imaginary number I. So it's J and then K. But to be in W, right, to be in W, the B, C, G, D, H, and J, right, B, C, D, G, H, and J need to all be 0. So what I have in W looks like this. A, some variable A, and then 0, 0, and then 0, and then some variable, some number F, and then 0, and then 0, 0, and then some number K. So do you see I have 3 free, I know I didn't set up a system or anything, but do you see how I have 3 free variables, A, F, and K? Right, I can replace A, F, and K with any number I want. And the other variables, B, C, G, D, H, J, those were fixed. Those were basic. They only took on one specific value for any replacement of A, F, and K. They had to be 0. So I have 3 free variables, A, F, and K. So there's going to be 3 vectors in the basis in a basis for W. All right, and just as I've been doing, I'm going to take the way a general vector in W looks like, and write it as a linear combination. I'm going to spread it apart based on the free variables. So one involving A, right? So A times, and then what are the coefficients of A as I go through here? 1, 0, 0, 0, 0, 0, 0, 0, 0. The coefficients of A throughout that 3 by 3 matrix, plus then the free variable F times, and then what are the coefficients of F throughout this? 0, 0, 0, 0, 1, right? 0, 0, 0, 0. And then plus, and then K is the other free variable, and then what are the coefficients of K throughout this? 0, 0, 0, 0, 0, 0, 0, 0, 1. All right, so every vector in W, every matrix that's in W can be written as a linear combination of these 3 matrices. All right. So I'll write that set again. All right. So the set with this matrix with the 1 in the upper left-hand corner, and this matrix with the 1 in the middle, and this matrix with the 1 in the lower right-hand corner. This spans W. Right? Every vector in W can be written, as we've seen here, as a linear combination of these 3. And then to check if they're linearly independent, I'd have to say, when is this linear? Now, then there's more than 2 vectors this time, right? So you actually have to check. If I were to take this linear combination here and set it equal to the 0 matrix, right, the 0 vector, where all 9 entries are 0, and say what values of A, F, and K would give me the 0 vector, can you see that only, I'm not going to do it all, can you see that only the trivial solution would work? Only A equals 0, F equals 0, and K equals 0 would make these all add up to the 0 matrix? Right, and that is the case, right? So when you set this equal, any linear combination of these three equal to the 0 matrix, the only scalars, the only A, F, and K that make that true would be the trivial solution 0, 0, 0. Right. And it's because the non-zero entries of these matrices don't have the same position, right? That's really why that's the only way that's going to work out. So spans W and is independent. All right, again, you can more formally put that out. So this guy here is a basis for W. All right, this set with these three vectors, these three matrices. So the dimension of W is 3. Right, is a 3. So the set of 3 by 3 diagonal matrices is a 3-dimensional vector space. Right. Wonderful. All right, so there's a lot of examples there, but again, you may have noticed I approached them all the same. I was given a subspace of a vector space, asked to find a basis. I took what does a general vector from the larger vector space look like? What conditions would need to be met for that vector to be in W, right, to be in the subspace? And usually working through those conditions creates a system of linear equations. And that system will have, some basic variables, some free variables, and you should be able to write every vector in the subspace as a linear combination where the weights, right, the coefficients, the scalars in those linear combinations are the free variables. All right. And so the number of free variables will give you the number of vectors in a basis. And yeah, that's what I did. That's basically what I did for every single one of these examples. And then the dimension, of course, is the number of vectors in that basis. All right. Wonderful. All right, so hope this wasn't, this was a lot. It's a lot to take in. These are pretty heavy concepts, talking about basis and dimension and spanning and independence and vector spaces, and it's a lot of heavy stuff. Lots of things to check, lots of things to do. But I'm sure the more and more you practice it, the more and more you read about it, the more you're exposed to it, the better you'll get. And it's just like with anything. All right, so enjoy practicing all this stuff. I hope you have fun with it, and thank you for watching.